Hello everyone, my name is Łukasz Bratasz. I'm head of Cultural Heritage Research Group at the Jerzy Haber Institute of Catalysis and Surface Chemistry, Polish Academy of Sciences in Krakow, Poland. My research focuses on risk of mechanical damage to vulnerable objects to humidity and temperature variations in museums, libraries, and archives in general in memory institutions. But also I work on the risk assessment and energy efficient methods of climate control. But today I don't want to speak about my research. I would like rather to show how this research could be converted into practical tools supporting decisions of collection managers, conservators, designing preventive conservation strategies. And let me show now my presentation. As you can see here, these tools are made available on the digital decision support platform, which we also call digital preventive conservation platform, that offers the remote access and free access to quantitative risk assessment for heritage assets. And as I mentioned, my name is Łukasz Bratasz, and here is the email address you can use if you want to contact me. And motivation for this research is stated here, which says that effective risk management and preservation strategy requires identification, which is obvious, and quantitative assessment of the most relevant processes, which are in fact priorities leading to loss of collection value. And this statement, this motivation is very obvious between community working on the preventive conservation. But maybe if some of you have more experience with heritage science focusing on the technological history, I would like to give some examples how the quantitative risk assessment can be helpful in decision making. And maybe I will start to illustrate the use, the need for such a tools with one of the most important challenge for conservation community, for heritage community, which is energy consumption. And one of the most important question is how we really preserve the collections, the cultural heritage objects, but at the same time, we will not cause the harm to the environment. So how to preserve the collection, but at the same time, keeping energy costs, financial and environmental at the very reasonable and optimal level. And this graph shows the annual energy consumption expressed in kilowatt hours per square meter in 75 museums all over the world, but more or less in the same climate zone. This is the zone typical for the Northern Europe or for the areas in US like New York, Boston, Philadelphia, or Chicago. And as you can see here, some data are from my private database, which the data I obtained from my colleagues and friends. There are UK data from 2009 from the publicly available data. There is Arup data. This is the construction company, one of the largest construction company building museums all over the world. And there is a building performance database, and this result shows the data from the museums in New York, Boston, Philadelphia, and Chicago, as well as the data from Yale University, where I spent almost 4 years as a head of this, where I work at the head of the Sustainable Conservation Lab. And what you can see here, that this data covered, they span wide range of energy consumption, almost 2 orders of magnitude. So it means that really depends, the energy consumption depends on how we really control the environment. If we control in the very narrow bands of relative humidity, we use a lot of energy. If we have local humidifiers, simple solution, passive solution, we can use many, many times less energy. And I would like, so we know that we can save a lot of energy. But the question, of course, is what is another part of the equation? What is the risk to the collection when we relax the environment? And I would like to focus your attention on this data, which is the Yale University Art Gallery data, and show the climate. And as you can see here, here are relative humidity variation in the Yale University Art Gallery, which vary between 40 and 60%, which is the range recommended by environmental guidelines of International Institute for Conservation, as well as International Council of Museums Conservation Committee. And the relative humidity from this gallery falls mostly into this range, with some exceptions here as well as here. But the relative humidity variation is only the first very basic, very rough estimation of the risk to the collection. And much more important is to look at dimensional change, dimensional response of the wooden objects, which we call in this case strain. And it allows to evaluate risk of damage in better and more efficient way. And I will try to show you how to sample this climate using this painting from the collection of the National Museum in Krakow, where I also worked before leaving to Yale. And this is a tempera painting on 10mm thick wooden panel, varnished from one side. So it means that diffusion penetrates only from the back side, but the front side is blocked. And to analyze the strain history, the dimensional change history, we developed the computer model in the one of the typical softwares for finite element calculation. And we, of course, put a lot of relevant parameters, all relevant parameters, material parameters, and we calculated the strain. And here you can see data. Here there is a strain history, and the strain history is compared with the strain history in the gesso layer, which is the animal glue-based ground, which is the most brittle part of the paint layer. And it is the strain history in the gesso layer is compared with the critical values at which beyond which the gesso can be damaged. And as you can see here, the strain history is very far from any risk, and it means that there is no risk, and there is still a lot of room for relaxation of the environment without bringing risk of mechanical damage to works of art. So we know that the strain history is very good measure of the risk, but it has some drawbacks, this approach, because to do that you need large computers, because this calculation require large computational power, are usually time consuming. So even using the good computers, you need few hours for calculation and require specialized expertise and programs. And I have to say that I know I don't know if I know any museum which has this competence, but large museums, leading museums in the world, at least they have the network of collaborators, so they have access to the expertise, and for them this risk could be calculated. But the medium-sized or smaller museums, or the museums which are not leading museums, they have really there is a barrier in access to this expertise. Therefore, we proposed an alternative approach, which is based on the website platform. So the user uploads the environmental data, temperature, relative humidity data. Climate is decomposed into elementary sinusoidal range variation using a fast Fourier transform. And there is a large database for which the elementary strain variations are calculated in response to each sinusoidal range variation. And this database it sees on the website and is collected there. And this elementary strain variation were pre-calculated for the sine functions of various amplitude, of various duration, but also on various levels, for different types of the objects, for different types of the woods, for different thicknesses, for different direction of the moisture diffusion for different gestos and for different temperatures as well. And when this climate is decomposed, then knowing the elementary strength variations which are practical data and stored in the database, they could be called and fused into complete object response. And the benefit of this approach is that the strain history can be calculated within few seconds. And so this is the motivation, and the herie.pl, we call this digital preventive conservation platform herie.pl, available for everyone for free at the address herie.pl. So please use, you just only to register. And this database, this website, this preventive conservation, digital preventive conservation platform was developed within the IPERION HS project, which is focused on integrating platforms for European research infrastructure or heritage science, and it was developed with the financial support of the Getty Conservation Institute. And as you can see here, there is a few institutions participated in the development of the database, but also another institution participated, contributed to the conceptualization of the platform, and so on. The structure of the platform follows the framework of 10 agents of deterioration proposed by the Canadian Conservation Institute. So those 10 agents are incorrect relative humidity, incorrect temperature, fire, criminals and vandals, pest, contaminants, radiation, water, physical forces, and dissociation and curatorial neglect. Those agents which are highlighted in the white, they already contain the tools for estimation of the risk. Those which are gray, we are waiting for the new tools to come. So far, we have 6 modules, 6 tools. One is mechanical damage due to the environmental variation, and we have 3 types of the objects, like the restrained wood, panel paintings, and the parchment. We have tools for chemical degradation. So generally, we calculate the risk due to the depolymerization of the polymers, and we have the damage function for paper developed by Matthias Terlitz and his colleagues, Mikalski for general materials, and Image Permeance Institute for cellulose acetate. And we can calculate in this model both the relative lifetimes, frequently called also lifetime multipliers, as well as the lifetimes for those materials. We have module developed for risk assessment of fire, and the data and conceptualization was done by the Jean Tétreault from Canadian Conservation Institute, but my institute, Jerzy Haber Institute, developed the calculation engine for it. And we have module predicting indoor concentration of damaging gaseous pollutants from external sources, developed within the European project Impact. So what you need to know is just a material which was used to construct your museum and the concentration in the outer air, and from that you can calculate or estimate levels indoors. So it is tool for the small user which doesn't have the indoor instruments equipment measuring the concentration. We have light damage calculator developed by Stefan Mikalski from Canadian Conservation Institute, which is based on the single point measurement and extrapolation. And now we have also new refined version of the light damage calculator developed by Eric Hagen from the Canadian Conservation Institute. In near future, new tools will be available as well, like indoor generated pollution module developed within the European Commission project Memory by David Tickett and his colleagues. We will have full finite element modeling for mechanical damage, as the module which I showed you has some limitation. So for example, it cannot be used in the very warm climate, or humid climate. So if the temperature is above 30, our module so far doesn't work, so it significantly overestimates the risk. And we plan to develop also the module which would enable user to calculate the soiling of objects and surfaces by indoor particle pollution and deposition. We have also new module for upload and processing environmental data, and particularly this processing of environmental data was broadened, so the user can upload 2 data sets and combine them, which reflect and then evaluate by other modules, for example, risk of mechanical damage. And this situation reflects the situation when one museum loans the object to another museum. So you combine the climate from the loaning institution and from the place where the object will be exhibited, you combine, and then you can evaluate the risk. So this module was particularly developed for registrar working in the museums and making decision about the loans. So far, a few words about the users. So far, the main users are collection managers and conservators. Heritage scientists is quite a large group, but surprisingly for us, also educators. Educators teaching students, making courses, they use the tool extensively. So far, we have almost 400 unique users and around 1,800 files were uploaded, data containing climate data. And here is the list of the institutions which supported financially development of the platform, and I would like to thank them all. And so I finished my presentation, but if you agree, I will show you the tool itself, how it works. So what you need to go to the website herie.pl. You need to register, but I'm already registered, so I just need to log in. And I'm here. Here is the front website of our platform, and you go to the modules. This is the tool, the front page again with the 10 agents of deterioration. So when you click select, for example, incorrect relative humidity, you can select mechanical damage or chemical degradation. Let's go to mechanical damage. Here are the data which I previously uploaded. So let's select one of the gallery from the National Museum in Krakow. You can image, this is temperature variation, and this is relative humidity variation, and you can see here that there was a dry spell of frosty period during which the relative humidity dropped significantly in the gallery. So we can evaluate the risk to this object. So we proceed to the calculation. We can perform new calculation. We can select out of the 3 categories of objects like painting on wood. Then we have selection of the different species. Let's select the Italian poplar. We have the cut of the panel. Tangential direction is more risky to the object, so let's work with that. And let's select, for example, thickness, like 20 millimeters. Calculate long-term mean temperature and mean relative humidity. I propose to leave it as it is when you have the object, when the object stays in the same space for a long time, and you can select the different type of the gesso. Let's go for the stiff gesso and moisture diffusion for the one phase, and we can proceed to the calculation. And you see here that we still need to few seconds for engine to calculate the risk. Here it is, it's calculated. We can show it on the plot, and here you can see the strain history, and now we compare it with the damage criteria. And as you can see here, even this object didn't respond to this drop. So even the relative humidity didn't follow the specification, but the risk for this object was negligible. There was no risk, in fact. So this is the mechanical tool. I think it would be also good to go for a moment to chemical degradation. you can calculate relative lifetime for this space. And as you can see here, that here is the average relative humidity, average temperature, and relative lifetime is close to 1. Relative means comparing to the condition, to the lifetime in the condition 20 Celsius degrees and 50% of relative humidity. So more or less, this is as in a museum, close to 1. But you can change and calculate what would be the lifetime if we decrease temperature to 15 Celsius degrees. And you can see here, the relative lifetime increased to number almost to 2, in some cases more than 2, and in case of cellulose acetate 1.9. So you double the lifetime of the collection if you decrease temperature by 5 Celsius degrees. And let me go now to light damage calculator, and I will go to the light damage calculator number 2, which is our new development. You can calculate, you can look at the light damage due to the uploaded data, but I will not do that. I will go just without selecting the database, the light history. And here what you can see here, you have a relatively long list of the materials which were tested and measured by Eric Hagen from the Canadian Conservation Institute. You selected this, for example, dye. So the database contains information about the synthetic dyes used in the textile industry. Here you can have some information. For example, you can look into archival information about the pigment. So this is the book with the dyes which was used for the test. So you can have this information as well, easily available. Then you have the calculator for the current dose, so the prior fading and future dose. So let's select here 100 megalux, and when we move it here now, you can see here that there is a color change. So this is the original value, this is the fading, and this part is the static, so it's compared to the grayscale color difference standard, which is used by it's the standard. And here you have dynamic part, which is comparison of the color change, and here is the blue standard, blue 1, 2, 3, and 4. And as you can see here, it varies when I changed those. It varies significantly. We have also information about the fading curve. We have the 2 different spectra, one measure for the original object, and this is for spectra of the dye which faded. We have also information here about, we can select because the previous information was just for 1 day, but if you have, for example, collection or the object with several colors, you can select from the list here and then see how all these colors change according with the increasing light dose. We have also some information about all dyes, but also about statistics. So how many of the paintings are super sensitive, how of them they are medium sensitive, and how of them they are relatively stable. So that was it. I think my time is running out, so please use the platform. We encourage you. You just need to register and use freely. Thank you very much.